Hello everyone, my name is Robert Strandh and the title of this talk is Call Site Optimization for Common Lisp. The context of this work is the SICL project, and you can read more about this project at the link that's given on this slide. The SICL project, SICL nowadays means SICL implements Common Lisp. The purpose of this work is to lower the cost of function calls in Common Lisp. And there are several reasons why function calls in Common Lisp are kind of expensive. And here are some of those reasons. Late binding, optional parameters and keyword parameters. Callee must often check types of arguments. The arguments must be boxed. If the callee is generic function, it can be dynamically updated. And multiple return values complicate the caller, and we will talk about these each of these issues a little bit more in detail. Late binding means that callee can be modified, can be redefined, or can become undefined after a caller has been compiled. And the way this situation is usually handled is by having an indirection through a symbol, which is the name of the function. And that indirection is altered when one of those situations occurs. In SICL, it's also handled by an indirection, though it's not through the symbol, but in a particular function cell in a first-class global environment. Late binding is no longer respected when there's a compiler macro or inlining. The specific reason for compiler macros and inlining is to avoid the cost of these calls, but the price to pay is that late binding is no longer respected. Optional parameters and keyword parameters also can introduce additional cost for a function call. If there's an optional parameter, at least the argument count must be checked. It must be checked in most cases unless the lambda list is an entire rest argument. And the conditional branch is necessary to determine whether a callee should initialize the optional parameter from the argument or from the form in the lambda list. Keyword parameters are even more costly because for each keyword parameter, the callee needs to find the first keyword argument that matches. And unless the lambda list contains allow other keys, then the provided keyword arguments must be checked for validity. And there's an exception to that case, which is when :allow other keys, the keyword argument :allow other keys was supplied with a value of true. The cost of keyword arguments and optional arguments can be mitigated by the use of compiler macros. But as we said previously, compiler macros no longer respect late binding. In general, the callee must check the types of all its arguments. There are, of course, cases where it's not necessary when any type is required. But consider, for instance, if the callee is the function car, then it has to check that the argument is either nil or a const cell. Again, this type of this cost can be mitigated by inlining, but again, the late binding will no longer be respected then. In general, all arguments must be boxed, which means that raw values such as raw floating point values or raw integers cannot be passed as arguments. They must be wrapped in some kind of object that tells which type it is. And that's necessary because we don't always know the type of the arguments. Consider, for instance, a call to map car. elements of the list passed to mapcar could be anything that's available at runtime, and we don't know the types of them at compile time. There are ways around this requirement that arguments must be boxed. For instance, one way around it is to have multiple entry points for each function, so that one entry point accepts boxed arguments and another entry point accepts unboxed arguments. And in particular, that technique is used in Allegro Common Lisp. And they also use a similar technique in order to avoid boxing when there's a single unboxed return value. For generic functions, since they can be dynamically updated, the caller of a generic function can make basically no assumptions about what methods of that generic function are applicable. Multiple return values complicate the caller because, in general, the caller must check that the callee returned at least as many values as the caller wants, and it must pad with nil if there are not enough arguments supplied by the callee. And this cost can be mitigated by recognizing that most callers require at most one single return value. And what the callee can do is then to always set some valid return value, which could be nil then, in the first register used for return values. That way, a caller that requires a single return value does not have to check the number of return values, and it could just access the return value in the pre-agreed upon register. So the purpose of the current work is we propose a general technique for call site optimization, and that technique can handle many of the issues that we previously discussed. So in terms of previous work, to our knowledge, no work on call site optimization has been published in the context of Common Lisp. And in the paper we discuss three techniques that have been implemented but not so much published. And those are inline caching, CTORS, and sealing. And sealing and inline caching are not call site optimization techniques in this meaning, even though they improve performance of function calls, just like inlining and compiler macros do. So we will not discuss those here, but we will discuss a technique called CTORS. CTORS were introduced by Gerd Mollmann into CMUCL in 2002, and the same technique has since been included also in SBCL and CLASP. And there's a similar mechanism used in Allegro Common Lisp. CTORS can be used for certain functions that are often called with some arguments being literals. In particular, it's used in CMUCL and SBCL for the function makeInstance, which is usually called with the constant name of the class. And in the CLASP implementation of Common Lisp, CTORS are also used for functions such as change class and reinitialize instance. So the way CTORs work is that a compiler macro is defined that replaces the original call by a call to what's known as a funcallable object. And that funcallable object is specific to the literal arguments that were given by the call. This funcallable object is typically created using the form load time value, so that it's available lexically at the call site. And then this funcallable object is, of course, communicated to something that we could call the call site manager that knows to update the funcallable object when the callee changes. So the call side manager modifies the funcallable instance function of the funcallable object when the callee is altered. So for instance, for make instance, those alterations of the callee could consist of changes to the class definition of the class being instantiated. So we can sum up the CTORS technique by saying that it's accomplished by the manual creation of a compiler macro. There actually has to be a definition of a compiler macro for this technique to work. And there is also an additional indirection through the funcallable object. In order for the callee to be called, first a call is made to the funcallable object, and then the funcallable object calls the sum code of the callee. And the technique that we present here can be seen as an automatic and low overhead version of CTORS. For this talk, we're going to talk a lot about function calls, and we're going to define a function call in the context of this work to be the code that accomplishes the following tasks. It accesses the arguments and puts them in a place where the call protocol expects them. It accesses the function object indirectly, probably through a name. From the function object, it accesses the static environment, which is what happens when you have a closure. Then there are objects in that static environment that the callee needs to know about. From the function object, it also accesses the entry point, which is typically the address of the first instruction of the code. And then it transfers the control to the entry point, usually with an instruction such as jump to subroutine or call or something like that. So it saves the return value, the return address on the stack or in a register. And then upon callee return, it accesses the return values in the place where the callee puts them, and it stores those return values in places where they're needed for further computation. In a typical Common Lisp implementation, the function call is implemented this way. The compiler generates the code once when the caller is compiled, and then it's never changed after that. But since the callee can change after the caller has been compiled, the two must respect what's known as a function call protocol, which means that it puts the arguments in pre-agreed upon places, and the callee puts the return values in pre-agreed upon places. Our technique can be used when the name of the callee is known statically, and we recognize three different cases in our paper. The first case is when we have a function form where the operator is a symbol naming a function in the global environment. The second case is a function form where the operator is the symbol funcall, and the first argument is either a literal symbol or a function special form with a function name in it. And the third case is a function form where the operator is the symbol apply, and again the first argument is either a literal symbol or a function special form with a function name in it. There are other possibilities that we might consider in the future. For instance, we could consider using handling mapcar or some other functions that are typically called with a constant or constant function argument. For the purpose of this talk, we're only going to consider the first case, that is the form with an operator that is a symbol naming a function. The other cases are handled in similar ways. So this first case is also called an ordinary function form in the Common Lisp standard. Our technique consists of the code emitted by the caller is is an unconditional jump instruction, and that's all there is to the call. The address field of the jump instruction is filled in by the callee. And the code for the function call, according to the definition of function call we just talked about, is contained in an object called a trampoline snippet, or just a snippet. And the snippet ends with a second unconditional jump instruction that jumps back to the instruction following the first unconditional jump instruction. We can illustrate the constellation of the caller, the callee, and the trampoline snippet as in this figure. So this is the memory of the heap, and we have the code for the caller here, and somewhere in here is a call site. And the call site has an unconditional jump instruction that goes to this trampoline snippet here. And there's some code in here in the snippet that typically, but not necessarily, calls the main body of the callee and then returns back here, and finally the snippet ends with an unconditional jump instruction that goes back right to the instruction following the first one. So the callee is able to adapt the contents of the snippet according to the characteristics of the callee. In particular, when the callee changes, then the snippet can be altered in order to take into account new properties of the callee. But there's some situations where some default snippet is allocated, and that happens when, for instance, a new caller refers to an undefined callee. We load some code that calls a function that hasn't been defined yet. And the default snippet is also allocated when the callee is in the process of being redefined, or if it's made to be undefined. And the default snippet essentially contains the same instructions as the standardized function called protocol would require. So we can illustrate the default snippet this way here. We have again the code for the caller, the unconditional jump to the default snippet, and the default snippet starts by accessing the arguments from the stack or the registers of the caller and puts them in the pre-agreed upon places. And then there's a call instruction that transfers control to the callee, and at the end of the callee there's a return instruction that returns back here, and then there's the code that processes the return values so that they are put in the places where they're required for further computation in the caller. So for this technique to work, the caller has to provide a certain amount of information to the callee. It has to provide the name of the callee, the number of arguments, the type of each argument, and for each argument, whether it's boxed or unboxed, and for each argument, its location, which could be in a register in a stack position. And it must provide information about return values. We're not going to discuss the return values any further. There's more information in the paper. So the callee can take advantage of all this information to lower the cost of the function call in several different ways. First of all, fewer indirections are involved. In fact, call can be directly to the body of the callee without any indirection through a symbol or a function cell. If the callee is not a closure, then the static environment does not need to be loaded, so another memory access is saved. Argument parsing is greatly simplified, especially if there are keyword arguments that are literals at the call site. Then the callee can access the values of those keyword arguments directly from registers or from the stack of the caller and put them in the places where it needs them. So no argument parsing is then required. Unboxed arguments can be handled this way, much in the same way as multiple entry points would handle the same thing. That is, the callee could have special entry points for unboxed arguments and just jump directly to such an entry point. And in fact, in some cases, the entire callee can be inlined into the snippet. So for instance, if the callee is the function car, then the entire code for the car function could be inlined into the snippet. So there's not even a call instruction required. Now, car is, of course, a bad example because it could always be inlined since it can never be redefined anyway. There are a few disadvantages of our technique. First of all, it's fairly complicated. We need to define a call site manager that needs to analyze all this information supplied by the caller. There are two unconditional jumps, and that might seem costly, but in fact, unconditional jumps are nearly free with modern processors. Our technique complicates the garbage collector a little bit because the position of the snippet and the position of the callee and the caller in memory must not change as a result of garbage collection. Luckily, this is already the case in the SYCL garbage collector for the global heap. And another complication for the garbage collector is that snippets must not be reclaimed when they're still on the stack being used. In terms of future work, our technique has not yet been implemented, so in fact we haven't been able to test how much benefit there is to it. So the first step in future work would be to create a native executable for SYCL, probably using only default snippets to start with. And then after that, implement the remaining details of our techniques. And that sums up my talk. We would like to thank these people for their remarks on the paper. Frode Fjeld, who read some early versions of the paper. Dave Murray, same thing. And Dwayne Rettig, who helped me understand how Allegro Common Lisp optimizes certain call sites. So thank you very much, and if there are any questions, I'll be happy to answer them.